thanks to organizers of the meeting, Dr. Kurushkin and Professor Tseri, and thanks for excellent organization, which we all enjoy. So my lecture today is called not periodic law in science, but periodic law in chemistry and other science. I shall speak about, first of all, about periodicity as a phenomenon. Second, I shall speak about the periodicity of objects that are different from atoms, which are ions, isotopes, molecules, and so on. And the last part of my lecture will be applications or attempts of application of periodic law in biology. So first of all, let us speak about periodicity. What is periodicity? So we have at least three different definitions. First definition is very strict, and you can find it in the handbooks of mathematics. So you can find the periodic function. So this is simply function, and this is periodic function. So function which are at the period t and times is repeated. So it is very strict definition, and we shall follow it so that we shall compare chemical periodicity with this mathematical periodicity. Second is our daily intuition. So what is periodicity? At least we can look at the clocks, we can look at the pulse, we can look at the tides, slow, high, and then we can look at the phases of moon. So we can look at the salary which we receive periodically, and so on. So all this daily intuition phenomena, they are also periodic. And at least the chemical periodicity. So we can look at the handbook of chemistry and find something strange, that the properties of elements are in the periodic relationship to the atomic weights, or we can say atomic numbers of the elements. Let us look what this means. So you know that in English, this very strange language, the table has two meanings. Yeah? Table is tablica and table is stol. So this is periodic table. So periodic table of Theodore Gray. He made a big table from wood, and here there are things that can be opened, and inside there are elements. So good place for keep different elements. And if we look what is inside the table, we shall see that only small portion of elements are not metals. All other are metals. These are metals. All they are fill all this table. Okay, if all the elements are, or most of elements are metals, we should think a little bit about some metallic properties. Yeah? So this is from well-known film, and this is properties of metals which we should investigate. Okay, what is the properties of metal, typical properties of metal? They must conduct. What conduct? So you conduct warmth, electricity, sound, and maybe expand somehow. So let us put here at the x the parameter like atomic mass or atomic number, and at the vertical line we shall apply the property which is thermal conductivity, electrical conductivity, sound conductivity, or thermal expansion. So it is better visible, so better like this. We can look at the properties and trying to compare these properties with the saw or sinusoid from mathematical definition. Is there any periodicity here? No. So this is very strange curves. So they does not resemble any sinusoid. Maybe the properties I have chosen are very bad properties. Maybe we should choose another properties. Okay, this is the hardness. This is hard and soft are letters in Russian language. So this is boiling point or melting point. So let us look what is here. Hardness, it means you take element and try to destroy another element. And that's why you build the scale of hardness. No periodicity, no. So boiling, something like periodicity, but also nothing. And here melting point, also no periodicity. It's very strange because we believe that all these properties should be periodic somehow, but they are not periodic. Okay, you can put a question. Mendeleev has predicted the melting point of gallium. Here, how he did this with all this aperiodic function. So now, for example, with the help of Excel table and so on, so for the students, there is a task to predict gallium. So they fail. They completely fail. But you see, there are trends which Mendeleev somehow felt very well. He predicted melting point, and he also predicted density. It is specific weight. Let us look at the density. Here we look at the density, and these charts, you can see the balls, and the radius of ball is the density, for example, or molar volume, or radius of atom. And if you look here, we can see very clear situation which resembles our sinusoid. If we look at the molar volume, there can be a very small weight of a piece of uranium which will overweight the piece of lithium. So also this periodicity and radius of atom, also periodic function. At least these three functions are periodic. Okay. And what else is periodic? Let us consider, for example, the ability of atom to give electron or to pick up electron. So to give electron is a ionization potential, and to pick up is electron affinity, and we can compare this with quite normal animals like fox and crow. And so who are the most stupid crows who left electron very easily? Of course, these are alkali metals. Who are most clever foxes who pick up electrons? So these are halogens. So if we draw the chart, we can see that these properties are also periodic in the same sense as previously. The same is true for electron affinity or for electron negativity, so which is a combination of electron ionization potential and electron affinity. Okay, we feel something, that some properties are periodic, some properties are not periodic. And now, what actually was done by Mendeleev? He drew this sinusoid, or something like sinusoid, like something like so. What is this? these are lower valency and high valency. And these are valencies of hydrides and oxides. So maximal valency against hydrogen and against oxygen. And this property, it is not the same as physical properties. It is the property of knowledge about element that we have. So it is also periodic. So let us resume. There are such properties which are connected with size of atom or radius of atom. This first. Second, the ability to lose or to find an electron, and the valency. So these three properties are really periodic. And this curve is approximately what we need. How can we obtain this curve? This is sinusoid, and this is 1 divided to x, and superposition of them give us something that is decreased. So we can imitate by mathematical methods this curve. But so next is n, and this is up to now it is 7 periods where we can do this. And the last is very strange thing, is the t. It is not a constant. It is very strange, extremely strange. Imagine the wheel of roulette, yeah, which should be every time at the same position, but it is every time at another position, yeah. Remember, for example, consider a moon that is every day not at the same position, but a different one, yeah? Or imagine that you receive salary not regularly, once per month, but once per month, once per 2 months, per 3 months, and so on. So you can see that this value is not a constant, and this is the reason why new and new versions of periodic system appeared, yeah? So, and this problem was somehow recognized by Mendeleev, but it is not fixed at all. It is quite another phenomenon. So, let us look at the properties not of elements, but of simple bodies. Simple body, for example, we wish to consider allotropic modifications of elements. Yeah? These are possible allotropes. Those elements all have allotropic modifications. So most familiar to you are diamond, graphite, and something like buckyball and so on. So we can think, but cannot say that these are periodic functions. For example, this is the chart temperature against pressure. And this is chart for gallium. Suppose Mendeleev lived not on the Earth, but he was on the Pluto or on Jupiter. So another value of pressure. So look, here is gallium on Earth, here is another gallium with another melting point. So he would predict another melting point of gallium. Suppose Mendeleev made prediction of phosphorus. Maybe for some reasons phosphorus was not discovered at that time. He would call it eka nitrogen. Yeah? and write a letter that he found that it should be red material and deep red and so. And experimental chemist can send him a message that phosphorus is quite another compound. It is lightening in the darkness. So you understand that up to now it is an unanswered question, and the question whether the allotropes can be constructed, the periodic system of allotropes is quite open. Periodic system of ions. Okay, let us consider this law. This law graph, and this will be the ionization potentials of atoms. Now let us ionize every atom. From here, we shall go to here. Let us ionize 2 times, 3 times, etc. And every time the chart, the graph will be exactly the same, only with one difference. It will be shifted by unit to the left. So this means that periodic system of ions exists. It is exactly the same as periodic table of neutral atoms. Yeah? We can say that this is neutral atoms, and this is halogens, for example, and minus atom, negative charge, will be in this column, and here sodium will be in this column. So the periodic tables of ions are approximately the same as they are for neutral atoms. So let us go to isotopes. Isotopes are different by the number of neutrons in the nuclear. And this girl is trying to see one or another isotope. This is the beginning of the periodic table of isotopes, or we don't know whether it is periodic or not. Here is the number of nucleons, here is the number of neutrons. And if we would like to draw it, it will be very, very large. Yeah? You know, Moscow University is at the top of the hill, and probably the wall of the Moscow University will be not enough to indicate all the elements. But they are separated at the special blocks or periods according to magic numbers of nucleons. So the first person who mentioned this was Russian physicist Selinov. It is his book, and he published this as the chart. He was a secret physicist in Landau Institute of Physics, and he drew this chart that looks like periodic. So simply, so curve is approximately this one. He can do also the circle from it, and so on. And he was not allowed to go abroad to publish his results. He worked at the table. So this book appeared only in 1970s. And if we look what happened in the other world, so in Nobel Prize in Physics was given to Gilbert Meyer and Jensen, just approximately for the same things. So for levels which explain why this or that number of nucleons is magic. So one fresh example, or not very fresh, but relatively fresh. So people start to examine clusters of metals which go through the channel of mass spectrometer. And these clusters had different charge, and these clusters has different number of atoms inside. And a big surprise for scientists was that some clusters of alkali metals, for example, or alumina, so they are quite stable, more stable than the others. And the number of electrons, like a magic number, was completely the same for alumina, for sodium, and so on. So these elements are called like super elements, and or clusters with magic electron count. So this is the work of Fanao Kong from China, 1980s. He thought about the periodic table of diatomic molecules. He thought quite logically. So valence electrons should be responsible for their properties. Indeed, when he considered the table based on valence electrons, he found quite exciting things, and they are like sinusoid. So the only problem that Fanao Kong met was the content of this cell. So for example, here he would like to put one molecule with 14 valence electrons. He took 7 and 7, it is nitrogen, 2. But he also can take CO, because it is 6 plus 8, yeah? Or boron and fluorine, it is 5 plus 9. So all these molecules, all three molecules, will be in the same cell. So nevertheless, Kong observed this periodicity and published. And this is Ray Heberlin. So this is very warm person. I worked with him. He published a paper, a lot of papers, and a book on the problem of how to express graphically these diatomic molecules. And for example, this object he considered to be the periodic table of diatomic molecules, so that its projections on different positions give you periodic tables. And another work done by him is the three-dimensional projection. So he considered that this is a four-dimensional object which can be projected. But anyway, if he collected a lot of data on diatomic molecules, of the molecules that exist or not exist, and so on, and he observed the same sinus-like properties. This is Bolderev. He is quantum chemist, and he made very careful analysis of diatomic molecules. So he constructed 120 first and second row diatomic molecules and arranged them along the X, where the number of valence electrons will be. So you can see that here is the letter. This is sigma, pi, and so on. And this is the degeneracy of the level. And you can see how complicated, how complex is the problem. For example, analogs like, analogs like carbon and silicon, they have difference in Bergenian C. So that molecule carbon C does not reproduce the electronic configuration of carbon 2. And so it's complicated structure, and we can see that not so simple is the task. So all these calculations somehow confirmed by experiments, and that's why this is how diatomic system of periodic system of diatomic molecules looks like. This is Nikolai Morozov. He's very famous in Russia. He's called Russian Leonardo. Why? So he was 25 when he wrote a poem against Tsar family, and immediately he was imprisoned in the, not far from here is Schleswig Tower. So he was there, and he spent in the prison 25 years. But his brains were very active. He immediately, after appearance in the prison, he asked the soldier to bring him Bible, the same book, and start to analyze. And he write on the pieces of papers huge 2 volumes book about the chronology of Biblian events. And now it is analyzed by Russian historians, and it has been considered as correct thing. So I shall not speak about this. And also he did something in geology, in physics, and so on. And one important book he wrote in the prison was the book which is called Periodic System of Molecules. So look, here is periodic table of atoms, and here is periodic table of hydrocarbons. So if it is chlorine, this is C2H5. If this is fluorine, it is methyl. And if it's oxygen, it is methylene, and so on. So what was his main achievement? That he published this table in the time where Ramsay has not done his work yet. Morozov discovered that every period of alkanes or alkenes is finished with saturated hydrocarbon. But there were no such atoms, and he immediately sent messages that this equivalence, analogs of hydrocarbons should be searched for and should be discovered. And then when he got information that helium, argon, neon, and so on, they are really exist in nature, he was very happy. And after that, after 25 years, he returned from the prison. So everything was changed. There was a Soviet Union. No, not Soviet Union. I'm sorry. It is later was Soviet Union. He met Mendeleev. Exactly the last year of his existence, and he showed this book to him. It is quite a huge book. It is nowadays in libraries. And Mendeleev asked immediately to give the scientific degree of Doctor of Science to Nikolai Morozov. And we can only guess what happened then, because at the day when Morozov wished to meet Mendeleev, Mendeleev died. So, somewhat later, there was a lot of work published by Shemyakin, and he claimed the classification of molecules based on molecular number. It is approximately the same thing as Kong was used for the atomic molecules, but Shemyakin used it for all molecules. So he draw these properties and do some predictions and so on, but this was not very well known. So another book, if you search for, is the book of Polish scientist Górski, who declared this normalized oxidation degree for molecules and classified molecules according to this principle. Now, another rules are well known, like, for example, Hickel rule, which is for n plus 2, and you can multiply the number n and so on, and you will get stability or instability. This is also something similar to periodicity. So something analogous is in the chemistry of boron hydrides, and it is called weight rule. And one more thing is the work of Diaz. Diaz considered the periodic table of hydrocarbons. So, for example, these 4 isomers of hydrocarbons can be transformed by surrounding of hexagons only to exactly three variants of structures. And these structures can be transformed again to only 3. And he constructed the very long table of hydrocarbons which are similar to their parent structures. So, and there is a book which you can find, and this is periodic table of hydrocarbons, and so a series of papers of Diaz. This is my contribution, and I published this in 1980s and 1990s, and it is something like Babaev constructed hyperperiodic system. But this is the principle which is on the background of the system is another. So we consider that these are valence electrons, these are atoms, and if we construct the plane where in every point there is enormous amount of molecules appeared, here and here there is nothing, no molecules with valence electrons at all. And we can consider this as a poles, as organometallic pole or inorganic pole, and so on. And consider strong acids to be located here, strong bases to be located here, and so on. And these are amount of molecules in every point of this space. And these are isotopes. And my goal was to analyze what similarity exists between these isotopes in vertical position. And as a result, this is the version of hyperperiodic table. And this is only the representative sample. Only one molecule is represented, because actually here is enormous amount. But if you can see this, this value is corresponding to alkanes, this to alkanes, this to alkenes, and so on. So you can understand what is the meaning. Now, let me very briefly speak about the application of periodic law in biology. So here is Beklenish, is famous Russian biologist. He spent his life on constructing or finding the natural system of organisms. But you see the principles which are in between, inside this approach are very complicated. So they are similar to any periodicity in molecular sense. Another person who very deeply considered this problem was Alexander Lubitsch. He is a very famous Russian biologist, and this is the book by Daniel Granin in Petersburg. It is called This Strange Life. And this person, when he was 18, he promised himself that all his life he will devote to the construction or finding of periodical system of biological organisms. So actually, when he was 17, he died. And people start to analyze his archives and are very much surprised. And so, finish? Yeah? So, but Lubitsch did very important thing. He compared his statements with the periodic system. So he told that there are different systems, hierarchical, combinated, and correlated. And one sign has a dominant value, all other are correlated with it. It is very clever conclusion about the periodic table of atoms. So Vavilov, another biologist, he paid attention to this O. So that these plants are analogous to these plants, but they are shorter. And so he decided to make predictions of how to improve the how it is called, harmony. So, and when he entered the Congress of Biologists, so everybody stand up and said, so these are biologists, welcome their Mendeleev. So these are another example. This is periodic table of arthropoda. This is this animal or some living being, which is found in the geological stones, and the person classified this arthropoda, and this was very predictive system because he told which examples are not found yet. This is another periodical system in biology. So these guys tried to put the size of ears and size of tail on the same chart, and suddenly they saw that something changed, and changed quite regularly. So the principle is really working. And this is the last slide. This is biological isomerism. This is Professor Urmantsev in Russia. He's studied isomerism in nature So what is isomerism in nature? He looked at the petals of, so imagine, second petal is here or here, third is here or here, fourth is here or here, and so on. And he drew all the possible combinations and found, surprisingly, that the number of combinations is exactly the same as in the as in monocyclic sugars. The same he did for leaves. They are quite different, quite similar, but the so later. And the end was that he made actual parallelism between living systems and, for example, molecules. So, and here is his book, Symmetry of Nature and Nature of Symmetry, so published in Russian. So I made quite a lot of statements, but I think you can believe me that the periodicity as a principle has some future.